Hello friends, so today we are going to solve 5 questions, and these 5 questions are from electrostatics. So the first question, we are given 2 parallel sheets, each have large area A and are separated by a small distance. The surface charge densities are sigma and minus sigma. You wish to pull one of the sheets away from the other by a small distance x. How much work does this require? So in this case, we have to find out the amount of work done which is being required. And for that, we are going to find out the force that is required, and because distance we already know, and that is going to give us the work done. So we can just approximately draw the figure. So we are having 2 sheets, and this is sheet which is having a plus sigma charge density, and there is other sheet, and these are very close to each other, and it is having a charge density of minus sigma, and A is the area of each sheet, and distance between the two is given as very small, so we can just neglect it, and they are oppositely, so obviously they are going to attract each other. And let us suppose for the lower one, we move it by a distance of x, and we are going to find out amount of work done. And for that, first of all, we are going to find out the force, and that is going to help us to find out the work done because we know the distance. Okay. So we know that these sheets we can take as an infinite one. So we can say the electric field due to an infinite sheet of charge. So we can say the field due to infinite sheet of charge, and that is our E sheet. Then this E sheet will be equal to just charge density divided by 2 epsilon naught. And so if you want to find, we can also find out the charge on each sheet. We are only interested in one sheet. Okay, so we can say that charge on one sheet, and let us put that charge is given as Q, then Q, this will be equal to our charge density multiplied by the area. And this E sheet will be the electric field because of, suppose we call this as sheet number 1, and this lower one as a sheet number 2. So the E sheet will be the electric field because of sheet number 1 on the sheet number 2. Okay. So therefore we can find out the attractive force. We can say attractive force, and that force is, let us suppose, our F. Then this F will be equal to total charge and our electric field. Okay. And we substitute charge is equal to our sigma A, and this is our sigma upon 2 epsilon naught. So therefore we get that the force will be equal to sigma square A, and this is our 2 epsilon naught. Okay. Now we can easily find out the work done. So we can say that our work done, because this will be attractive force. Okay. So we are going to do the work against the force, and that work done is suppose our W, and that will be force multiplied by our X. So it comes as a sigma square A 2 epsilon naught times X. Okay. And same we can see, we can also solve this by using the energy formation also. Okay. So let's try that also. And so this is a second approach. And in the second approach, we are going to find out our work from our this electric field energy. Okay. So we start with that electric density of an electric field, sorry, energy density of electric field. Energy density of electric field. Let us suppose that is given as U. Then this U we know is our half epsilon naught and E square. Okay. And we know that between the sheets, the electric field is our sigma upon epsilon naught. So we substitute value of electric field, and this gives us that our energy density U will be equal to over half epsilon naught sigma upon, one second, yeah, E square is there, yeah, and this is our E square, and it comes as our sigma square upon 2 epsilon naught. Okay. Now as it is going to move through a distance of x, okay, so we can find out the change in stored energy. Okay. Because as it is going to move, there will be a change in the volume of the field region. Okay. So which basically means we can just draw it approximately. So this was our initial volume that in which the field was existing, but now we have pulled it downward by a distance of x, and this is now the lower sheet. Okay, so the volume is our this one, and this is our change in volume, that is our delta V. Okay, so we are interested in this delta V. So we can write that our change in stored energy and for that, like I said, we will be requiring the volume. So we can say that pulling the sheet by x, increasing the volume, increases the volume of the field region. Okay. And this increase is our delta V, and delta V nothing but our area multiplied by our x. Therefore, we can write out the increase in field energy. We can say that our increase in field energy, and let us suppose that is our delta U, then delta U will be equal to our original energy, and because of this increase in the volume. and we know both our u as well as delta v, so we can say our delta u is equal to u is our sigma square upon 2 epsilon naught, and this becomes a times x. Okay. And this is nothing but our work done. So we can say our w is equal to our sigma square a 2 epsilon naught times x. So in both cases we are going to get the same result. Now we come to the second question, and second question is comparatively easy, and it states that there are no other charged particle in the vicinity. At what distance below a proton would the upward force on the electron equal to the electron's weight? The mass of the electron is about 9 into 10 to the power minus 31 kg. So here the question is rephrased in a little bit complicated way, but it is all about the equilibrium of the forces. And physics, more or less, maximum chapter you will find will be all about the equilibrium of the forces. If there is no equilibrium, so either there will be torque will be there, or some kind of acceleration will be there, some kind of angular acceleration will be there. Okay, if everything is in equilibrium, all the forces should be balanced. And balanced forces are going to produce necessary result. Okay, that can be any kind of acceleration, or we can say change in direction, something like that is bound to happen. So in this case, we are given that we are having a proton and we are having an electron, and let us suppose the distance between them is given as r. So obviously they are oppositely charged, so there will be force of attraction between them, and this electron is going to have a downward force. Let us call this as our Fg. Okay, and this Fg will be balanced by the electrostatic force. Let us call this as Fe. So everything is equilibrium, so we can easily find out this condition and satisfy the condition that Fe is equal to our Fg and get the answer. Okay. So we can say that gravitational force which is nothing but the weight of the electron. So we have Fg is equal to over m times g. Okay. And then we have our electrostatic force. Electrostatic force, that is our Fe, and Fe is our 1 upon 4 pi epsilon naught, and this comes as by E square and divided by R square. And in equilibrium, okay, we can say the balance condition our Fe is equal to our Fg. Therefore we can write that our mg will be equal to 1 upon 4 pi epsilon naught E square upon R square, and we are interested in finding out our R square. So we can say that our R square will be equal to 1 upon 4 pi epsilon naught E square, and this is our mg. And we simply substitute the values, and 1 upon 4 pi epsilon naught is our 9 into 10 to the power 9. Charge we know is our 1.6 into 10 to the power minus 19, this is whole square. And mass is given to us, mass is our 9 10 to the power minus 31, and g is our 9.8, and this is our R square. and this will be approximately equal to, and we can say this is nothing but our square root of 26, and we can approximate that this is equal to over 5 meters. This was much more easier, only the statement was a little bit lengthy given to us. And this type of question we should have done many times, but here the values are given in a different way. And if you look closely, you can clearly understand that the only representation of values are different, but the solution is comparatively easy. So it is given that two volleyballs mass 0.3 kg each, tethered by a nylon strings and charged with a electrostatic generator, hang as shown in figure. What is the charge on each of, assuming charges are equal? Okay, basic figure is given to us. So let us take a vertical, and with respect to vertical, this is angle theta, so other side will be also theta, and the distance between the two is, let us suppose, this we are taken as r, and this total height is, let us suppose, of h. Please remember, this height is given as a vertical height, it is not a slant height. Okay, in the normal questions usually this is given as a slant height. Okay. And slant height, let us assume, is our L. And with respect to vertical, if we pull it downward to the one side, let us suppose this distance is our x. So x will be equal to nothing but our r by 2. So we can say that our each ball is displaced by, suppose that we have denoted it x, and that will be equal to r by 2, and r is our 0.5 divided by 2, and this gives us 0.25 meters. Okay. And now we can easily find out our slant height L. So we can say that our L will be equal to h square plus x square and its square root. So h is given as 0.25, this is also, okay, so this is 0.25, okay, and this is 0.25 whole square plus 0.25 whole square and square root. So therefore we get that our length is equal to 0.25 square root of 2 meters, slant length rather. Okay. Now we can easily find out our theta. Okay. So we can say that our sine of theta will be equal to our x upon L. So x is our 0.25, L is our 0.25 square root of 2, and here this cancels out, so we get this as 1 upon square root of 2, that gives us theta is equal to 45. And okay, now we can use just our, let us suppose this is our ball A and this is ball B. So we take one of the balls now. So this is our ball A, so there will be a tension T, okay, and this angle will be over theta, so we are going to get this as T cos of theta, and here we are going to get T sine of theta. And on A, in the downward direction, we are going to have mg, and toward the right side we are going to have our electrostatic repulsion, because both are having same charges. So, and part B, there will be for ball B same everything, okay, but we can solve it only by using one ball, and if we can say in vertical equilibrium, in vertical equilibrium, we can write that our T cos of theta will be equal to our mg, and in horizontal equilibrium we can write that our T sine of theta will be equal to our Fe, okay, and we can just divide them, and so from here we get that our Fe will be equal to mg tangent of theta, and our theta is our 45, so this becomes a 1, so this is nothing but our m times g, and mass is our 0.30 and this is our 9.8, giving us 2.94 Newton. And for electrostatic, now we can directly substitute the formula, which is our k q square upon r square is equal to 2.94, and here we are interested in finding out the charge, so we can say q is equal to 2.94, and we have r square, so r is our 0.5 whole square, and k is our 9 into 10 to the power 9, and it comes as a square root. So this charge q will be approximately equal to 9 into 10 to the power minus 6 coulombs. Next question. Okay, so we are given that at each corner of a square is a particle of charge q fixed at the center of the square is a point of opposite sign of magnitude q, capital Q. What value must this capital Q have to make the total force on each of the 4 particles 0? And part B, with Q taking on the value you just found out in part A, show that the potential energy of the system is 0. Potential energy is comparatively, you can say, easy. We simply add their respective energies, and that is going to sort out the problem. But let us draw the approximate figure. So we are given a square, and let us suppose this is our A, B, C and D, and a charge of Q is each of the vertices having charge Q, and let us join the diagonals, and this is our point C, and it is having a charge of Q. So this is the basic figure, and so let us say that the side of this square is suppose A. Therefore we can say that this our distance of any corner to the center, okay, any corner is our R. So we can say that R is equal to nothing but A divided by square root of 2. So we consider that we have a square of side A and side A, so it means distance of, or we can say distance from the center. The center is denoted as C to any corner. And let us suppose that is our R, then this R will be equal to A upon square root of 2. Okay. And we are going to consider any one corner, okay, and we are going to solve for that. And let us consider that we are solving everything with respect to this corner A. Okay. Because that is, if it's true for corner A, then everything will be true for other corners also, because it is our symmetric part. So you can say consider corner A, and corner A is having a charge of our Q. Okay. So in the part A, we have to find out so that the net force is equal to 0. So we have this corner A, and it is having charge Q. Then there is a charge Q at corner B. There is a charge at C, which is also Q, and there is a diagonal opposite charge. Sorry, this is our D, and then this is C, which is also Q. Okay. And all are same, so obviously there will be force of repulsion. Okay. So let us take one by one. So from part A, we can say that we are going to find out value of Q for 0 net force. So like I said, for our charge A, this at D, C and B, all are going to have our repulsion forces. You can say that our repulsion from 3 corner charges, 3 corner charges, and we have, this is our A, so there will be force of repulsion, so this will be because of charge B, and this will be because of our charge D, and the resultant will be lying somewhere here, and this will be, suppose there F, and there will be also a force of repulsion because of our C, and this is FC. Okay. So first of all, because of the side this FB and FD, the magnitude will be same. Okay. So we can say force because of charge at B will be equal to force because of charge at D, and that will be equal to K Q square, and we have this as our A square. Okay. And we can easily find out the resultant. Between them we have a 90-degree angle, and therefore we can say, let us call this F net. So we can say therefore our F net will be equal to, this will be coming as square root of 2 K Q square upon A square. Okay. And then we have our FC, charge C. Therefore we can say that our FC will be equal to K Q square, and this is distance is our, and is whole square. So this comes as our K Q square upon 2A square. So the direction of this net force as well as FC is same, so we can just find out their net force, total repulsive force from the all the 3 corners. So you can say total repulsive force from all 3 corners. and let us call this as F repulsive. This will be addition of our F net plus Fc. So we get force because of this repulsion will be equal to k q square a square, and this comes as square root of 2 plus 1 by 2. And also we have a charge of opposite sign at center C. One second. Let us call this center as O. Okay. So center is our O. So because of this charge at center O, we are going to have a force of attraction, and let us call this as FO. Okay. So we can say that attraction from the central charge from central charge, that is our FO, and we can write that our FO will be equal to QQ, and this is our A square root of 2 divided by 2. We take a modulus because we are only interested in the magnitude part, and this gives us 2k upon a square q multiplied by q and its modulus, and its direction will be opposite to our this F repulsive. Because from the figure we can also see that F net plus Fc will be balanced by our F naught if we want that charge A should be at equilibrium. Therefore we can say that equilibrium condition and for that we can say FO is equal to F repulsive, and we can simply substitute the values. FO is about 2k upon a square, q times q is equal to F repulsive is k q square upon a square square root of 2 plus 1 by 2. And here this a square, this k and q square cancels out. So we get from here that 2 times q is equal to q square root of 2 plus 1 by 2. And this gives us that the q will be equal to, obviously, opposite sign. This is minus q by 2. And we have square root of 2 plus 1 by 2. So this is our value of the charge which is required so that we have the net force is equal to 0. And now we come to our potential part B, that is potential energy of the system. Total potential energy, or we can also call it electrostatic potential energy of the system. And we have 4 corners, corner interaction, and there will be 2 diagonals. Okay. So we can say that we are having 4 side pairs at distance A, and we are having 2 diagonal pairs at distance a square root of 2. Therefore, you can say that because of this diagonal, we can write this QQ will be equal to, and we have this as 4 because of the side pairs, and this comes as our Q square upon A plus 2 diagonals K Q square upon A square root of 2, and this gives us K Q square upon A, and this is 4 plus square root of 2. And then we come to the center-center interaction. Okay, I forgot to mention this one. This is corner-corner interaction. Corner interaction. And then we come to the center-center interaction. Center interaction. And for center-center interaction, we are having 4 pairs, and each is having at a distance of our, sorry, this is not center but corner center, my mistake. Corner center, and this is corner, yeah. So this is 4 pairs, each at a distance of A by square root of 2. Therefore, we can write this as U, capital Q and small q will be equal to 4 times K QQ divided by A square root of 2, and this comes as our 4 and root 2 KQ divided by A, and we substitute value of this capital Q. So we get this as our 4 square root of 2 KQ upon A times capital Q is our minus Q by 2, and this is square root of 2 plus 1 by 2, and this gives us minus K Q square, and this 2 goes by 2, and we can multiply it by inside, so this will be coming as 4. Okay, let me A, and this will be coming as my 4 plus square root of 2. So this is our corner center. Now we can simply add them. Total potential energy. Total potential energy, that is by U, will be equal to potential because of a corner plus potential because of the center corner, and their values are same but opposite sign. Q square upon A plus 4 square root of 2 minus K Q square upon A 4 plus square root of 2, and these two terms cancels out, so we get total potential energy is equal to 0. Okay. Next question. So it states that 2 positive point charges Q are located at point plus minus L 0. A particle positively charged Q and mass m is initially located midway between them and is then given a tiny kick. If it is constrained to move along the line joining the two charges Q, show that it undergoes SHM for small oscillation and find the frequency. So we are given that we are having two charges and there are of our this is our Q and other one is also Q. Suppose this is our center at the origin 0 0, so left side is minus comma 0 and right side is our plus a comma 0, and we are given that we are having a charge small q mass m, and it is also positive. And so let us assume this is also positive charge and this is also positive charge, and we assume that it slightly moves towards our right side through a distance of x. So therefore the distance between our left charge and new position will be our L plus x, and on the right side it will be our L minus x. And so we are going to have a repulsive forces between the two. So we can say that force due to charge at plus L force due to charge at plus L, okay. And let us suppose we call this as F positive, then we can write that our F positive will be equal to K QQ and L minus X whole square. Similarly, we can write force due to charge at minus L. Force due to charge at minus L, let us call this as F negative, and we get this as our F negative will be equal to K QQ, and this becomes L plus X whole square. Now we can find out the net force on the particle. Net force on the particle, let us suppose that is our F is equal to F negative minus F positive. So we will simply substitute the values. We get F is equal to K QQ, and this becomes 1 upon L plus X whole square minus 1 upon L minus X whole square. And for small oscillations, we know that value of X will be very much less than our L. Therefore, we can write that 1 upon L plus minus X whole square, it can be written as, we take this as a common, and this will be 1 minus plus 2x upon L, and this will be plus, and so on. And so we substitute in this expression and we get this as our F will be equal to KQ 1 upon L square 1 minus 2x upon L minus 1 plus 2x upon L. And this gives us, if you open the bracket, these two terms are going to cancel out, and this will be other terms, these two terms will add up. So we get our force F will be equal to minus 4KQ divided by L cube times X. Okay, and this is nothing but our, we can write in form of our motion equation, will be equal to minus 4KQ upon L cube times X. Okay, and this is our equation of SHM. equation of our SHM, which gives us that our double derivative plus omega square x is equal to 0. So 1:1 comparison, we get that our omega square is equal to 4k kq divided by ml cube. Or we can say that omega is equal to square root of 4k qq, and this is your ml cube. And if you want to find out our f, so that will be 1 upon 2 pi square root of 4k qq upon ml cube. If you want, we can further solve with 2, but that doesn't matter. Okay. And so this completes the question. We come to the next part. So in this question, we are given that 4 positively charged bodies, 2 with charge q and 2 with charges small q, are connected by 4 unstretchable strings of equal length. In the absence of external forces, they assume equilibrium configuration as shown in the figure. Show that tangent cube is equal to q square upon capital Q square. Basic figure is given to us, okay, and it is given that is making angle of theta with the horizontal. So this is our basic figure, and let us name that this is our A, this is our B, C and D. And let us assume that this distance is our D. Okay. So you can say, because it's a rhombus, so this AB will be equal to BC equal to CD is equal to DA. So you can say that our AB is equal to our BC is equal to our CD is equal to our DA is equal to our D. We have assumed it, and therefore we can find out the distance between our this BD and also the distance between our AC. Okay. So you can say that our AC will be equal to, this will be coming as, because this is our 90 degree and this is our D, so this will be D cos of theta, and the other side also will be our D cos of theta. So AC will be giving us 2D cos of theta, and similarly we can write our BD. BD will be giving us 2D sine of theta. So these are the distances. And now all these are positive charges, so all the forces will be repulsive forces. Okay, but for equilibrium they are connected with the string, so there will be a tension force, and that is going to balance them. Okay. So we are going to consider any one charge. So let us consider this charge at B. Okay. So we can say forces on charge at B, which is nothing but our Q. So first is our, because of this BD, and so this is our charge P and this is charge at D. So this BD is going to apply a force on upward direction, and let us call that force as FQQ. Okay. So we can say that force due to charge at D, and this is our FQQ, then this FQQ will be KQ square, and the distance between the two we already know is our 2D sine of theta, so this comes as 2D sine of theta whole square. Therefore we get that our FQQ will be equal to KQ square, and we have this as 4D square sine square theta. Okay, please remember we are calculating everything with respect to this B. And for this charge B, we are having two charges. One is our at A, other one is our C. Okay. And so this is our B. So A is going to apply a force, repulsive force in this direction. Okay. And let us call this as FQQ, and C is also going to apply in this direction. And let us call, because it is also FQQ. And therefore we can say that force repulsion force from two Q charges these two Q charges are at A and at C, and each with magnitude, and it is going to have a magnitude of FQQ will be equal to, because here we are in capital Q and this is a small q, so FQQ will be equal to KQ times Q, and this is our D square. And then we can just divide these two forces into their respective components. Okay. So this is our point B, and we have one force because of charge A, and this angle is given as theta, so we are going to have this angle will be also theta and this will be also theta. Therefore we can say that one component will be FQQ cos of theta, and there will be a vertical component that will be FQQ sine of theta. And because of this was our A and this is our C, so C also we can divide into two components. Magnitude will be same, so we are going to FQQ cos of theta, and we are going to FQQ sine of theta. And so at B we are having, we can say, three electrostatic forces. So this is our B, and all the three forces are in upward direction. One is our FQQ, other one is FQQ, and this is our cos of theta, sorry, not cos but sine of theta. And further we are going to have this FQQ sine of theta. So these are the three electrostatic forces, all are acting in upward direction. So this is also upward and this is also our upward. Now we come to our tension part, and same we are going to make for our this charge B. Okay. And so this is a charge B, and it is connected by string. So this is our tension T, and we can to other side also we have a string that is also tension T. and this will be angle theta. So we can also divide it into two components, that will be t cos of theta, and here will be our t sine of theta. And from the other side we are going to get this will be our also our t cos of theta, and here also t sine of theta, and this is still with respect to B. So therefore for B, in the downward direction we are having two forces, t sine of theta, and other one is also a t sine of theta. So this B is in equilibrium. So if B is equilibrium, you can say that net upward forces and downward forces should be balancing each other. Therefore we can say that our for equilibrium at B, we can write 2t sine of theta will be equal to, we get this as 2k qq sine of theta upon d square plus k q square, and this is over 4 d square sine of theta. Let this be equation number 1. And now we are going to consider another charge, and let us suppose that is our charge C. So we can say forces on charge Q at C. We can also take charge A, that doesn't matter, okay, because the result will be same. So in this case I am going to just draw the forces directly, and first we are going to have, so this is our B, and it is going to give F QQ, and this is our D, so this is also going to give us this is going to F QQ, and we can divide this once again into two components. So first component will be, this will be angle theta, so we are going to F QQ cos of theta, and because of this we are also going to get this as F QQ cos of theta. And the vertical components, we get this as F QQ sine of theta, and because of the other forces we are going to get also this as F QQ sine of theta. Okay, and then we are left with at charge A, this is charge A, and charge A will be also going to provide a repulsive force, and that repulsive force will be F QQ, and this is for charge C. Therefore we can say for charge C we are going to have all the forces towards our right side. So this will be because of charge A, and then we are going to have two forces because of charge B, and they are going to have same cos of theta, and then we are going to have this as our F QQ cos of theta. And similarly we can divide the tension also, and let us consider, so this is a C, so there will be tension T, and there will be tension T, and we can divide, this will be our theta, so we can get this as our T sine of theta, and here we are going to get t cos of theta, and this will be also a t sine theta, and this will be a t cos theta. So therefore, because of this tension, this is our C, and all the forces are towards our this left side. So we have our t cos of theta, and other one will be also t cos of theta. So if we want that our C should be in equilibrium, the horizontal forces should be balancing each other. So you can say for horizontal equilibrium, at charge C, we can write that our 2t cos of theta will be equal to 2k qq upon d square cos of theta plus k q square upon 4d square cos square theta. And this is equation number 1, and this is our equation number 2. Okay. So we simply divide equation 1 and 2. Now everything is solved. It only the lengthy calculation left. So we can say that our this will be 2t sine theta divided by 2t cos theta will be giving us, because this kq everything is going to cancel out with respect to d square, and we will left with our sine of theta plus q square upon 8 qq, and this comes as 1 upon sine square theta, and this will be our cos of theta plus q square upon 8 qq and 1 upon cos square theta. And we can further resolve it, and this 2t cancel out, so we get this as our sine of theta cos of theta, and this will be our sine of theta, and this goes by square, so we get this as our q upon 8q 1 upon sine square theta, and here also these two terms cancel out. Okay, so these two are different, and we get this as our cos of theta plus q upon 8q 1 upon cos square theta. And this is a quite lengthy calculation, but quite easy to solve. So let us take the LCM, and we get this as our 8q sine cube theta plus q, and this comes as our 8 small q cos cube theta plus capital Q, and this comes here as our 8q cos square theta, and this comes as 8 capital Q sin square theta, and this is equal to our sin theta cos theta, and this 8 and 8 cancel out, and let us cross multiply it. So we get this as our 8, that this is 8, and this will be over q sin cube theta, okay. And sorry, 8 and 8 cancels out, my mistake, and divided by this gives q cos cube theta is equal to, this is our 8q sin cube theta plus q, and this is 8q cos cube theta plus q, and let us cross multiply it completely, and we are going to get this as 8 capital Q small q, and we are left with this is sin cube theta cos cube theta plus q square sin cube theta is equal to, and on our right side we are going to get this as our 8, this will be q sin cube theta cos cube theta plus q square cos cube theta, and these two terms cancel out. Okay. So we are left with only q square sin cube theta is equal to small q square and cos cube theta, and we are at the final answer. We can write this as our tangent cube theta is equal to q square upon capital Q square. So for this condition, or for this value of theta, or by you can say ratio of their respective charges, the entire system will be in equilibrium. Okay. Only the calculation was lengthy, otherwise this question is quite simple. We have to take care of only the resolution of the forces. If we are able to resolve the forces correctly, okay, we will be able to solve these questions quite easily. Okay. So please remember that most of the physics is related with our equilibrium condition most of the time. If there is no equilibrium, then it will be accelerated, which can be you can see angular acceleration, linear acceleration, or change in direction, change in momentum. Something is going to happen if the body is not in equilibrium. If it is in equilibrium, then it is always about making the forces, or we can say dividing the force into various components and making them equating with each other. Okay, like we specifically in this question, we equated all the vertical forces were naturally balanced with each other, but we equated the horizontal forces, and because of that we were able to solve this question. So please take care of the component of the forces and their equilibrium. Okay, you will get most of the question based on that. So this completes all the 5 questions. Thank you.